Chapter is pretty straightforward. There's only two major concepts in this chapter. It's the conservation of mass, or mass balance equation. What does that equation look like? The rate of change of the mass within a control volume with respect to time is the rate at which it flows in minus the rate at which it flows out. If you have multiple, put summation on it. So you have a control volume and you have ins and outs. And then you also have an energy balance statement. Rate of change of energy in the control volume with respect to time is how it flows in with heat. They could have said in with shaft work, but the sign convention is it's out with shaft work, so we put a minus sign in front of that W. And for all the mass flows in, they can bring their enthalpy, kinetic, and potential energy all on a per unit mass basis, as well as going out with a minus sign, m dot exit. Enthalpy, kinetic energy, and potential energy all on the exit. Those big equations can be now applied to a lot of problems. A lot of problems. A lot of the problems are steady state. If it's steady state, what happens to this term and this term? Zero. And then you have a nozzle, diffuser, turbine, compressor, pump, heat exchanger, throttling devices. A lot of these are also one inlet, one outlet. If one inlet, one outlet, then mass flow rate in is equal to mass flow rate exit. Just dispense with the subscripts. It's just m dot. A heat exchanger could have two fluids, both coming in, both going out. So they could have four mass streams, two ins, two outs for a typical heat exchanger. Or for a mixing heat exchanger, you could have two fluids come in like that, mix, and go out. So, okay, two ins, one out. It's mixing. Okay. Sometimes they call that a direct contact. The two fluid streams directly contact each other, mix, and go out as one fluid stream. There's some heat exchange. If one is cold, one is warm, they go out lukewarm. So that would be heat exchangers typically are not one inlet, one outlet. Throttling devices, one inlet, one outlet. Pumps, one inlet, one outlet. Compressors, one inlet, one outlet. Turbines, nozzles, and diffusers, the rest of those are all primarily one inlet, one outlet. And then today we'll get to transient analysis. So there, you don't throw this term away. That's non-zero. So you can have some accumulation or depletion of mass within the control volume. You fill an empty tank, that's a process. Starts empty, ends full. The tank is the control volume. Boom, you need to have that left-hand side, both in the energy as well as the mass equation. A shell and tube heat exchanger is used to condense steam. The steam enters the shell side of the heat exchanger at so many pressure, quality, and kilograms per second, and it leaves a saturated liquid. Sometimes we'll draw a heat exchanger like this. We'll put a separation on it. We'll call this the hot side, and we'll call this the cold side. The fluid stream comes in and goes out on the hot side. Maybe it comes in at 1, goes out at 2. The cold fluid maybe comes in at 3 and goes out at 4. This would be a counterflow type of heat exchanger. It's a preferred arrangement for the configuration. You can also have some other types of heat exchangers. Well, sometimes they'll draw a heat exchanger like this. They'll have a tube running like this, and then they'll have another side like this, goes like that. And what they're showing you is the tube, the flow goes through the tube, and then on the outside, the flow goes through the shell. Goes like that and goes out. So a shell and tube heat exchanger. So that's the terminology here on the shell side of the heat exchanger. But that just means the other fluid is not mixed with the other fluid because it's inside of a tube that runs through the shell. Okay, let's just add some numbers here. So it's pressure at 1 is 0.3 bar. The quality at 1 is 0.95. The mass flow rate of the hot fluid is 2.5 kilograms per second. And it leaves a saturated liquid. So the quality at 2 is 0. Okay. Why did I just say, hey, that the fluid that's condensing, the steam that's on the shell side, that condenses. It goes out as saturated liquid, right? Why is that the hot fluid? Wouldn't that be the cold fluid? I pause. I let you really think about that. Some of you are saying, of course it's the hot fluid. In order for it to condense, heat is going to have to be transferred out of it in order to get it to condense. That's the direction of the heat transfer. The hot fluid will have less energy content as it exits. The cold fluid may come out warmer. The cold fluid will have more internal energy as it exits. Lake water flows through tubes, enters at 21 degrees C and leaves at 31 degrees C. It's lake water, right? Knowing a little bit about those temperatures, they didn't say anything about the pressure, but it's coming from a lake. What do you think the pressure would be? Lake atmospheric pressure, about 100 kilopascal, right? Do you think that water is going to stay in the liquid phase all the way through that heat exchanger? Sure, it's not even close to 100 degrees C. It just went from 21 to 31. So it picked up some heat, then it went dumped back into the lake. They don't want to put really hot water back into the lake because of fish and birds and other things, right? Or they don't want to dump the hot water back into a river because of fish and birds and wildlife. Nor into a bay where they have power plants. Usually they dump the thermal waste into some water and then throw it back to the environment. In Texas, we build lakes by our power plants. We make our lakes by our power plants. I think somebody told me the state of Texas has only one natural lake in the whole state. The rest of them, man-made. Yeah. So you make some lakes. You use that for cooling water. You have one side of the lake. You dump warm water in, make it go and circulate all the way through to the other side, pick it up when it's cooled down, and put that back through again. And our lakes are huge by our power plants, so it's not like it's going to be doing that very quickly.
Is that a fact? There's only one natural lake?
I think it is. Does anybody know the name of that natural lake? Caddo? C-A-D-D-O? Where is that? East Texas? Let's continue on. Determine the rate of heat transfer from the steam. So that's our first question. We want to calculate maybe Q dot for rate of heat transfer, and it's from the steam. We introduce a control volume. You can do this for a control volume. Just do the hot fluid side. That's it. The hot fluid side, CV right there. Now we go ahead and apply for that control volume. Mass balance, M dot H is equal to M dot H all the way through. It's just the hot side fluid comes in and goes out. So that's doesn't change anything. But the energy balance, we have at steady state is equal to Q dot from the steam. Now if it's from the steam, just put a minus sign there because it's going out of the control volume. You have superseded, right? You've superseded the sign convention because of an illustration, and you've shown the direction of that heat transfer on the illustration. I didn't really label it that well, but Q dot right there from the steam. Is there any shaft work? No. And we have the mass flow rate. It comes in at state 1, so in at 1, out at 2. In with kinetic energy 1, out with kinetic energy 2. In with potential energy 1 minus potential energy 2. The changes in potential, nobody told me, but they are negligible. So I would assume that. Should maybe just be clear about it, say over here. Here's my assumptions. The changes in potential energy are 0. Changes in kinetic energy, I'm just going to assume the kinetic energy is negligible. The change in kinetic energy is negligible. So this all boils down to the rate of heat transfer from the steam is equal to the mass flow rate of the hot fluid or the steam through the system times it comes in with high enthalpy, goes out with lower enthalpy. And you just have to get the enthalpy at 1. That's the enthalpy of steam at the pressure of 0.3 bar and a quality of 0.95. Those two pieces of information allow you to get that true? Isn't that equal to H of F plus quality H of Fg? And then the enthalpy state 2 is H of F, saturated liquid, steam pressure is equal to 0.3 bar. Did they ever really tell me exactly that the pressure on the inlet is equal to the pressure of the outlet of the hot fluid? No, then just say that the pressure at 2 is equal to pressure at 1. I have to assume it. But it seems reasonable. A lot of times unless there's a restriction, the flow just flows freely through our pipes and there's negligible pressure drops. Now, when you have a pump, the purpose of the pump is to create a huge pressure gain. When there's a turbine, there's a huge pressure change across the turbine. But things like heat exchangers, the purpose is to promote heat transfer, not change the pressure of the fluids. All right. So you can calculate. I'm going to run out of space, so what I'm going to do is I'm going to say, I think you can chase those numbers, and you can calculate that this is 5550 kilowatts. That's from the steam. Maybe I want to continue to add that subscript from the steam. What's the part B? What's the flow rate of the cooling water? So what symbol do I want to introduce? M dot CW. So the mass flow rate of the cooling water. I'll do, you could do it a couple ways. Since we already did the energy balance on the hot side, you can do it just the energy balance on the cold side. If you do an energy balance just on the cold side, it's steady state, it's Q dot into the cold water, okay, or the cooling water, plus the mass flow rate. It flows in at 3, out at 4. And I'm going to neglect changes in kinetic potential energy on the cooling water change, okay? So does that look good for an energy balance? And so the mass flow rate of the cooling water is equal to the rate of heat transfer into the cooling water divided by the enthalpy change, H3 minus H4 of the cooling water. Now that change in enthalpy of the cooling water you can do two ways. You can just look up H3 approximated as H of F at the 21 degrees C, saturated liquid at 21. Agree? And then H of 4 is H of F at 31 degrees C. That'll be good, right? So you get those two values of H. And you come in, what's going into the cooling water is the same as out of the steam. I like long subscripts. I like to be clear about what is this Q dot. If it's coming out of the steam, it's the same as what's going into the cooling water. The heat exchanger, by nature, don't transfer heat to the surroundings. They transfer heat within the boundary of that heat exchanger between the two fluid streams. Sometimes, if I haven't said it already, it sounds like an oxymoron. It's an adiabatic heat exchanger. What? Adiabatic meaning no heat transfer, but it's adiabatic with respect to the surroundings. Adiabatic heat exchanger. Okay. So if I use those numbers, what we calculate is that the mass flow rate of the cooling water comes right in at about 132.6 kilograms per second. Now, I put 4 digits on that because there's another way. We could use the table A19, specific heat for water, liquid water, and we could say that H3 minus H4 is the specific heat of liquid water times T3 minus T4. Could we not? Let's say you do it that way. Well, I think in that table A19 they do have saturated liquid, water is at the very bottom, and they have it, it bounces around a little bit. So it's 4.18. Okay? So if we use a specific heat of 4.2 or 4.18 or some value like that, you can see already that I'm not going to get 4 digits of agreement if I can't get the specific heat to good to 3 digits. So it'd be a little more approximate. But if I do that, I come in with the mass flow rate of the cooling water is about 132 kilograms per second. And I think I used the value of 4.2 kilojoules per kilogram degrees C for the specific heat for liquid water. It's very good. Both ways are very good. Yeah, and you know what? I should have had this subscript changed. It should be 4 minus 3 because it's going out hotter at 4, right? Sorry about that. If you just look at the sign, I had to switch this H4 minus H3. Sorry about that. 4 minus 3, 4 minus 3. Temperature 4, which is higher than temperature 3. 4 minus 3. You would get a negative answer, and then you'd say, which direction is my heat transfer? Into the cold fluid? It's into the cold fluid. Yeah. Okay. Sarah, your question again?
For more intensive properties, when it's a subcooled liquid, when we look at the table, it's always going to be the saturated.
Yeah, that approximation that we use.
That's like back in chapter 3.
Chapter 3. So enthalpy is maybe a function of temperature and pressure, but we approximate it as a function of temperature only, and we use the saturated liquid, so we neglect the effect of pressure when we're confident that it's subcooled liquid. Don't try this in the superheated region, two-phase region. No, but when we're confident it's a subcooled liquid, then you can get a good estimate of H, very good estimate of H, just by looking up H of F at that temperature. How many students will do this? They'll say, isn't that the same as H of F at the pressure, ignoring the effects of temperature? All right, and there is a difference. Let's just solve problems. Warm airstream at 32 degrees C, 1 ATM, and 55 cubic meters per minute mixes with cool airstream. So we have 2 airstreams. One is warm, one is cool, and they mix and they go out lukewarm. And so the temperature, let's call this 1, 2, 3. So those are our 3 states. And we have the temperature at 1, 32 degrees C, pressure at 1 ATM. The volumetric flow rate, that's AV1. It's 55 meters cubed per minute. Then it mixes with T2, 15 degrees C, P2, 1 ATM, and the volumetric flow rate, 120 meter cubed per minute. For air, use a constant specific heat of 1.01 kilojoule per kilogram Kelvin if you need it. The mixed air pressure comes out at P3, 1 ATM. So everything's 1 ATM. No pressure drop through the system. Determine the mass flow rate of the warm air stream. So they gave me the volumetric flow rate, but what's m.1 in kilograms per second? Right. So what you would do is you say the volumetric mass flow rate at 1 is equal to the mass density at 1, AV1, or AV1 divided by specific volume 1. Either one, because specific volume is reciprocal of mass density. All right. How do I calculate specific volume 1? Air, it's air. Ideal gas equation all the time, right? It's equal to RT1 divided by P1, and if you want to use this R is R bar divided by the molar mass of air. So that's R bar divided by the molar mass of air. Okay. And so you would substitute numbers to get the specific volume of 1. After you've done that a few times, it gets a little tedious. Actually, I didn't calculate that. I calculated rho, the reciprocal of that. And rho is 1.157 kilograms per cubic meter. All right, so I was able to calculate the mass flow rate to be 1.06 kilograms per second. Now, if I need that in subsequent calculations, I'll have 5 digits on that. But when I report it as my answer to Part A, 3 significant digits. But if I need it for further on calculation, it's 1.0609 kilograms per second. Part B now. What is the mixed air temperature? We're asked to find T3, the temperature at 3, T3. How do I find T3? Do an energy balance for the control volume. And if you do an energy balance for the control volume, I'm going to run out of room, so I don't want to start with the most general, but it's the mass flow rate coming in at 1, bringing with it its enthalpy, and I'm going to neglect kinetic potential energy. They don't give me any information about that. No duct sizes, stuff like that. And also the mass flow rate coming in at 2, bringing with its enthalpy at 2. There's no heat transfer to the surroundings. It's just a nice control volume like this. It goes out like that. So that's my energy balance for that control volume. Can you read that equation? Do you like the form of that equation? Does it make sense, hopefully? 2 ins equal 1 out. Okay. Now we also have to have our mass balance. The mass balance, it doesn't matter the order on these. You could have done the mass balance before the energy balance, but the mass flow rate in at 1 plus mass flow rate in at 2 is equal to mass flow rate out at 3. True? All right. If I'm looking for the T3, if I can get H3, I got T3. So really, I'm thinking I need that H3 right there. If I look at my energy balance, I just solved for m dot 1. We can do the same thing for m dot 2, which will come down here, allow us to calculate m dot 3, put that back up. So that's how I got m dot 3. And now I can solve for H3. And once I solve for H3, solve for T3 or something like that. So do it this way. How about this one? To try and get it as far analytically as possible, you can write it this way. M dot 1 C sub P, let me do it this way. M dot 3 is definitely M dot 1 plus M dot 2. So what I'll do is I'll substitute in there to get rid of M dot 3. And so then I'll write that M dot 1 times H1 minus H3 is equal to M dot 2 times H3 minus H2. Yeah, that's right. Do you see the algebra? 2 equations. Got it to 1 equation by substituting and getting rid of m dot 3 and then rearranged. Thumbs up if you agree. Thumbs down if you see a sign error. No sign error. Come on now, right? This is algebra, but it has to be done right. It's good? So the way I like to think of it, 1 is hot and 3 is warm. So is this a positive change? Is H1 greater than H3? Yeah, it is. I like positive entities. So really this is a description of what's coming out of the hot fluid. What is H3 minus H2? Well, H3 is greater than H2. M dot 2 is the cold fluid. This is what went into the cold. I can read this equation. If I just look at it, I can read it. It's as if 3 was separated into a hot stream part and a cold stream part, and they're at the same temperature. Yeah, I know that, but the mass flow rate of the hot, how much ever it was, is contributing to the out of the cold, or the not cold, out of the warm, and whatever flow rate of the 2 coming in is some part of 3 going out. So this equation makes sense. If I like to use the specific heats like they encouraged me to right here, then I can say that m dot 1 times C sub P of air is T1 minus T3 is equal to m dot 2 C sub P of air T3 minus T2. Actually, at this point, the C sub P's cancel, and I have an equation that I can use to calculate T3. It's a little bit of algebra, but it's equal to m dot 1 T1 plus m dot 2 T2 divided by m dot 1 plus m dot 2. Sometimes it's helpful to work analytically as far as possible in symbols without throwing numbers in. True? Now that I have that, I've already solved for m dot 1. I already have T1, T2. I get m dot 2. M dot 2 is the same way we calculated the other one, is 2.4512 kilograms per second. And I substitute numbers for T3, and T3 comes out to 20.1 degrees C. Agree? All right, what's the mass flow rate of the mixed air? Well, just add those up. M dot 3 is m dot 1 plus m dot 2. And what was the mass flow rate then? Did I not write it down? It's 3.512, too many digits, so I'll take that off, kilograms per second. That's the answer for part C. Last one, what's the volumetric flow rate of the mixed air coming out? What's AV of 3? Well, the volumetric flow rate's the mass flow rate of 3 times V3. Is that true? And V3 is found just like you found V1. It's equal to R bar T3 divided by P3 molar mass of air. And when you calculate the volumetric flow rate at 3, you can express it both as meters cubed per second, which is too big of a number, or you divide it and get minutes, so meters cubed per minute, and it comes in at 175 meters cubed per minute. .175 meters cubed per minute is the answer for part D. Step back a little bit. What is the volumetric flow rate coming in? 120 plus 55 roughly. Hey, did we make an error, or is this just a fluke of good luck? That if I added the volumetric flow rate of 1 with the volumetric flow rate of 2, I actually get the volumetric flow rate of 3, good to 3 significant digits. You see that? I went the long way, but is it just random numbers just happen to be that way, or is it actually pretty close that the volumetric flow rate is conserved? Because we have modest temperature changes and modest pressure changes, volumetric flow rate is a good surrogate for mass flow rate. In a lot of times in engineering calculations for a lot of problems, especially in HVAC, heating, ventilation, air conditioning systems, you just work with volumetric flow rates conserved. When really it's not perfectly conserved, it's the mass flow rate that's conserved. But as engineers, we know what approximations work. And volumetric flow rate can often be treated as conserved. And in this case, it's good to 3+ digits. It's good to more than 3 significant digits. Okay? Does that make sense? Start changing pressure. Don't assume volumetric flow rates conserved. All right. Any questions about this problem? So we had this is what I would call a direct contact heat exchanger. There was mixing in the heat exchange. The other one was there was a heat exchange with the material in between, so the fluid streams didn't mix. A more conventional type heat exchanger. All right. Now we're having a pump problem here. So a pump takes water from a lake. So here's our lake way down here. And it delivers it to a storage tank. So our storage tank is way up here, up on the hill. The inlet pipe is submerged 6 meters below the water level in the lake. So below the free surface of the water level, that's the inlet to the pipe system. 6 meters submerged. And the outlet is 85 meters above the lake water level. So if it's 85 above the water level, then it's 91 total from the inlet to the outlet. Okay. Also on the illustration, the distance that the pump is located above the water level is 2 meters, right? Or it's 8 meters above the inlet. The pump is located 8 meters above the inlet. It's up on some dry land right there. All right. Now, the water is discharged into air at the top of the tank. So this is just shooting out right here. It's now going to fall and fill the tank. There's a lot of reasons that you don't put the discharge down low into the tank bottom like this. Okay? Do you want me to talk about that right away? Let me talk about it right away. Let's say that you filled up the tank at the top, but your outlet to the pipe was up just like I show now. Okay? So now the water level is full up here. True? And then something happens. Somebody shuts the pump off, but somehow it's able to flow backwards through a centrifugal pump that's just sitting there. The passageways are open. It's just the pump used to run and sling it out and throw it around. That's how the pump worked. It actually could be a siphon. The water could suck back out, go through the pump, spin it a little bit, and you'd come back the next day and your tank would be empty. Okay? That's why they don't do that. Another reason is maybe there's a break. Somebody has a valve right here, they don't think about it. Either there's a break in the line or a valve somebody opens and all of a sudden starts gushing out. True? So often you don't submerge the outlet into a tank because what you dump into the tank, you don't want it to, unfortunately, inadvertently be sucked back into the system. And this is a classic thing too. As you'll see this, I'll have a water system. Here's my surface. Here's my well. I pump the water out of the well. It goes up into a good water tank, water tower, right? And so the water tower is sitting up here full of water. And the well actually, I'm sure, is going to splash it out at the top of the pipe. And then it'll fill up the tank. Okay. Because if anything ever goes wrong when you shut this pump off, you don't want it to suck it back out, the siphoning, and push it back into the ground. True? Does that make sense? Okay, the other one is the terrain is like this, then it goes like this, then it goes like this, and somebody, well, they don't go that high, but let's say it's up like this. And you have a truck up here, and he's got a water tank on it, and he's going to be in the pipe distribution system. He's got a fire hydrant here, and do you ever notice how they fill those water trucks? They got a loose little flapper at the top that does not go into the water tank. They do not put something into the water tank on the truck. And they have a big sign on it that says, non-potable. Don't put it in your pot. Don't drink it. Because once it goes into that water tank to then drive around on a construction site and spread it out, it's not drinkable. The tank could have contaminants and other stuff. Maybe they were spraying something else with surfactant in it, or a herbicide in it, or something else in it. It's not cleaned. Dust gets in there, everything else. So it's not potable. You ever seen that sign? Yeah, look around. So anyway, so if they would have stuck it all the way in, and then all of a sudden there would have been a break in the line, what would have happened because of the elevation difference? It would have sucked that right out of that tank and all the way back into the line somewhere, and would have contaminated your water supply. So there's a lot of little things that, as an engineer you look at. I know why they do that. I know why they do that. And often it's because of accidents that are rare, but 1 in 1,000, 1 in 10,000, you do have something go wrong. Okay? So that's why it's not unreasonable for this water pipe to stop at the top and just let it splash in. The water flow rate is 11 kilograms per second. So M dot is equal to 11 kilograms per second. And the pipe diameter, D, I can't write M dot. D is equal to 6 centimeters. The pump efficiency is 89%. Determine the power required to run the pump. Well, you're putting in power here, W dot power to go into the pump. Only 89% of it goes into the fluid. True? Where did the other 11% go? Whooping up the fluid and making it warm, which is not getting it converted into the mechanical energy of the flowing fluid. Non-useful. Or maybe it went into friction that got the surroundings around the pump warm. Okay? All right, so how am I going to analyze this to get the power required to drive that pump? What do you think?
Energy balance.
Energy balance and a mass balance. The mass balance is pretty straightforward, but for an energy balance, let's introduce a control volume. And in thermodynamics, we have a control volume, and when you take fluids, it'll be a Bernoulli's equation, but it's very, very, it's very, very similar. Bernoulli's equation. And at the end of this chapter, I think it shows you the analogy between the Bernoulli's equation of fluid mechanics and the energy equation here for control volume. But let's do our control volume, where it's going to cut right there, goes on the outside of the pipe, outside of the pump, comes down, and now we have a choice. See, I'm enclosing all of that with my control volume, and now I've got a choice. I have to be a little judicious down in this region about my control volume. Okay? I'm going to show you 3 potential control volumes. We'll analyze each of them. You could come down and just cut like that. Tempting. Very, very tempting. Okay? You could come down, hit this surface, go a little bit below the water surface, just a little bit, come all the way across, hit the lake. Bottom of the lake, bottom of the lake, bottom of the lake, bottom of the lake, come up, all the way across, just a little bit below the surface, and close it in. See that? See the difference in those 2 control volumes in the lake region? And there's one other one, I don't know what color I can show it in. Come down just a little bit above the inlet to the pipe and cut across. And then cut all the way through the bottom of the lake. Bottom of the lake, bottom of the lake, and then come across just like that. So we have control volume A, control volume B, and control volume C. Okay? Does that make sense? All those make sense? All right. Let me analyze control volume B first. B. Okay. So how does the water get into control volume B? I know how it exits. It's up here. It's just cutting across that boundary of the control volume. How does the water get into the control volume B? Not so sophisticated. Just rain, yeah. If there's no recharge to the lake, right? What's going to happen to the water level in the lake? It'll be dropped as I pump it out. Okay. So in a way, the fluid flows into that control volume across the top surface, downward, along the whole system. And the lake bottom is essentially impervious to water flow. I'm not getting water flowing across the bottom of the lake bottom, right? Does that make sense? That's why I put the control volume surface a little below the water surface. And as the water surface drops, I need to inch that down, that top surface of my control volume. Maybe it's not 6 meters above the inlet to the pipe. Maybe after a couple hours of pumping, it's 5 meters above or 4.5 meters above, right? But I would have to inch the control volume surface down if I start draining the lake. Okay, now we apply the conservation of energy or energy balance for that control volume. Steady state. Any heat transfer. We do have work, but it's coming in, and I'm going to put this right here. This is the pump, the energy coming, the pump. It's driving, let's say, a motor that turns that shaft that comes into this pump right here. So I'm going to say it's into the fluid. I'm going to make a distinction between the W dot electric to the pump and the W dot that's mechanical add to the fluid. And this is going to be 89% of W dot into the pump. Okay? So this is what gets into the fluid in the form of the mechanical energy. Where did 11% go? Heat, friction, somewhere else. All right. We have the mass flow rate in and mass flow rate out. This is all in at state 1, all out at state 2. So the mass flow rate, I have its enthalpy in, enthalpy out. Kinetic energy in, kinetic energy out. Potential energy in, potential energy out. All that makes sense? I'm going to have to limit you on questions. I know.
Where did the control volume B? How's the out way up top?
Well, the red is the same for everyone, A, B, and C.
Oh, okay.
Yeah, they're all the same up at the top. It's just the bottom in the lake region where you have some choices and you have to be careful on those choices. All right, so what about if it's lake water, then the enthalpy, H, for incompressible substance, H1 minus H2. Can I replace it by C sub P, T1 minus T2? Okay. Did I talk about the temperature change of the water? Negligible. So the change in H is 0. Make sense? All right, what about the kinetic energy coming in? Surface of the lake. The lake is big compared to the outlet of the pipe. So this part's negligible. The kinetic energy going out, that's 1/2 V exit squared. That's not negligible. What about the potential energy coming in? That's going to be rho GZ that it comes in at. Okay? And then this is going to be, I'm sorry, it's not rho. It's just GZ. And then you have just GZ going out. So let's put, instead of in, put 1. And then GZ2 going out. I'd have to introduce a coordinate system. It's you can introduce a coordinate system starting at the lake, fine. You can introduce a coordinate system where Z is 0 at the inlet to the pipe, okay? It doesn't matter. One of them, they'll both work. Let's pick. Which one do you want? Do you want to put it here where Z is measured up, positive upward from the bottom of the inlet? You can see for this Z1, what is it? 6 meters. And what's this Z2? It's going out at 91 meters. If everything's measured from the bottom, then the flow in is just a little bit below 6 meters, or just rounded off to 6 meters. So now, what does this equation look like? We have W dot into the fluid is equal to the mass flow rate times G Z2 minus Z1 plus 1/2 V2 squared. I know I have a negative sign that I flipped around over there because I wanted to something, on the left-hand side is equal to a lot of it on the right-hand side. But I'm going to pause. Does that equation look good? Do you see it? How you got it?
Yes.
Can you read it? The mechanical energy into the fluid because of the pump goes into lifting it, increasing its potential energy, as well as increasing its kinetic energy. Because when it comes out of the pipe at the top, it has some energy. It has some kinetic energy. So what we do is we go to the side and we say, well, what is the exit speed V2 at the top? How fast does it come out? You take the mass flow rate, divide by density volumetric flow rate, and that will give me here, take it in 2 steps. The mass flow rate is equal to rho AV. So the velocity at the top is equal to the mass flow rate divided by density area of the pipe at the exit. So what did we have for M dot? It was 11 kilograms per second. Density, 1,000 kilograms per cubic meter. What about the area? Well, it's a 6 centimeter diameter. So the area of the pipe on the exit is pi d squared over 4. I can calculate the speed at which it exits. Okay. The speed at which it exits is 3.89 meters per second, almost 4 meters per second. It's pretty fast. So now I can come down here and I have the exit speed right there. I have the elevation difference. So it's back to 85 meters. This elevation difference is 85 meters. It had to lift it up. And then you had the mass flow rate, 11. So let me kind of bust this up. 11 kilograms per second. This first component is 9.81 times 85. It's 833.9 plus 7.58. And that's meters squared per second squared. And it converts to so many kilojoules per kilogram. Essentially, it's 99% of the pump mechanical energy that went into the fluid is needed to boost the elevation, and roughly 1% is required to have sped it up. Okay, and so the W dot of the fluid is equal to 9.256 kilowatts, and so the pump power, you divide that by 0.89 and you get that it's 10.4 kilowatts is needed to drive that pump. That's the power needed to run the pump. Of that 10.4 kilowatts, 9.256 kilowatts went into increasing the mechanical energy of the flowing fluid, which was realized in bringing it elevation, 99% of that to raise its elevation, and 1% of it to throw it out the pipe at the high end. All right, what I'm going to do is I'm going to say that the control volume C will give you the same answer. It will definitely give you the same answer. Yes, sir.
So I just remember for Cal 2, if the level of the lake is dropping, the pump has to work harder to move the liquid. Does this
if Z2 minus Z1, so if Z1 goes down, then it becomes closer. Instead of 85 meters, it may go all the way to 91 meters, where you have to pump it up 91 instead of 85. So it's going to take more energy.
So we're just assuming we're moving such a small volume that that isn't going to change?
No. No, look at here. This is 91 minus 6. If the pump level drops, it goes 91 minus 5. I mean, the water level in the lake drops. 91 minus 4, 91 minus 3.
Pumping the water out, would the level not drop?
The lake is big, so
Right,
we're going to...
So we're assuming the level doesn't drop.
That's right.
Okay.
Yeah. Okay. If you go to control volume C, all you did was you say the flow across that boundary is still going to have negligible kinetic energy coming across the top boundary at C. When you come over here, it has the same kinetic energy going out at C. This Z2 minus Z1. Okay, but one thing is the pressure. If you have to back up and look at this change in enthalpy. The enthalpy H1 minus, the pressure is not the same right in here. Back up a little bit. I should have done a better job on this H1 minus H2. Is H1 minus H2 is equal to U1 minus U2 plus P1V1 minus P2V2. Is that the change in H? Yeah. And so if you have negligible change in temperature, then definitely the change in internal energies are 0. Now I take a look. The specific volumes don't change. It's incompressible. Liquid water, incompressible. But P1 and P2 were the same for control volume B because they were both atmospheric. But if I look at doing it for control volume C, then the P at the inlet coming in, right there, is not any longer atmospheric. It's rho GH in the lake. So it's added 6 meters. So the work in the fluid, W dot fluid, is equal to the mass flow rate times the pressure 1, which is rho G let's say Z1. It's not Z1, is it? It's 6 meters. It's the depth that it's below Z of the lake level, lake water level, lake level. Okay. But the minus the P2 is atmospheric pressure, P0 atmospheric. So that P2 is 0. So you have to have this contribution here. You'll still have minus the kinetic energy exiting the pipe, and you still have the gravitational potential at Z1 minus Z2. Running out of room. And you'll get the exact same algebra. It'll be the same result. The last one, control volume A, which you said I'm just going to cut it real close and come around the pipe, the inlet to the pipe right in here. The problem with that control volume is, what's the pressure at the inlet to the pipe? Is the pressure at the inlet to the pipe hydrostatic below? Is it 6 meters of hydrostatic head? Is it rho GH, which H is 6 meters? The answer is no. Otherwise, it's not going to flow to the inlet of the pipe. And there's actually a suction. That pressure is lower. So this one is harder to work. So ignore it. Go with the larger control volume down in the lake region. transient analysis. So with transient analysis, you have a non-zero left-hand side to the mass balance equation. The rate of change of mass in a control volume with respect to time is not zero. But the right-hand side is the same. You have the mass flow rate in minus the mass flow rate exit. Same with the energy equation. You have the rate of change of energy in the control volume with respect to time. That term is not zero. It's steady state. It has been, but now it's not zero. It's equal to the rate at which it flows in with heat, shaft work, mass flow rate in, bringing with it enthalpy, kinetic, potential energy in, minus mass flow rate exit, enthalpy, kinetic energy, and potential energy exiting. There's types of problems. Okay? One type of problem is you have a large supply line or supply tank that fills an initially empty tank. All right, so if I have a big supply line and I connect it over here with a valve, and a valve is initially closed, but I hook up a tank. The tank is initially empty. I then open up the valve. Fluid's going to flow from the high pressure, high temperature, whatever, supply line into the empty tank, fill it up. I'll shut the valve when it's reached the pressure that I want it to reach. Make sense? What you would do is select a control volume like this. You could put the valve in it. Often they put the valve in it because it's just isenthalpic across the valve. But what will be flowing in at this condition right here, let's say it's flowing in at 1. It'll be the pressure 1 will be the pressure of the supply line. The temperature 1 will be the temperature of the supply line. Enthalpy of 1, enthalpy of the supply line, specific volume, etc. It's all of the supply line. But if you have initially empty tank, what does this mass balance equation look like? It looks like the time rate of change of mass in a control volume with respect to time is equal to how it flows in. Is there any exit on the empty tank? Filling an empty tank? No. So there you go. This is an ODE. What do you want to do when you see it? Separate, integrate. So when you separate, you put the DT over here. Have we finished successfully separating? It is. This is a rate of flow in, and this is the mass inside the control volume, two different entities. We integrate, so we find that the mass in the control volume after the process, the filling process, when we shut the valve, that's state 2, minus the mass that was initially in the control volume when we opened it. Hey, if we opened it when it was initially empty, guess what that term is? If it's empty, initially empty, then that's 0. Is equal to the integral of m dot n dt. Now, you could plot the mass flow rate in as a function of time. It probably rips in and falls off rapidly. That's probably how it happens. It's not steady. It probably gushes in, and then as it starts to fill up, it's a lower flow rate coming in, true? But the trick on analysis is leave that as an entity by itself. It's an integral of m dot n dt. Let's go to the energy balance equation. For the energy balance equation, what does it look like? The rate of change of energy in the control volume with respect to time is equal to, often, I should strike it up here. It's no heat transfer. It's an empty tank. You're just filling it. It's adiabatic. There's no real promotion of heat transfer into this empty tank or from this empty tank. Is there any shaft work or anything like that? It flows in with negligible kinetic and potential energy, and there's no out at all. So what we're left with is it's m dot n hn. That's it? Yeah, that's it. How could the energy inside the control volume be realized, this storage? It's either the combination of internal macroscopic kinetic, macroscopic potential energy, true? Or you can write it as mu plus ke plus pe. Okay. Well, it's not like it's not a big flywheel in the tank. There's not a large macroscopic kinetic energy. And it's negligible. We're not interested in changing pressure, like pumping it up to high elevation. So this change in energy in the control volume realized as the mass in the control volume times the internal energy of the control volume, just mu. Now I have a great equation. I separate dt, put that over here. I integrate, and so the mass of the control volume when you close the tank valve, the final amount of internal energy in the tank, minus how much mass I started with the tank. Hey, didn't we say that was started empty? Sure enough, start empty. That's equal to this integral of h in m dot n dt. Did you follow all that so far? Now here's an observation that most of us wouldn't make by ourselves, but somebody says, hey, isn't this true? Oh, yeah, it is true. If I have a large supply line, if I fill a little tank off the large supply line, does the pressure in the supply line drop? It's a large supply line. It's not going to drop the pressure in the tank, or the supply line, right? How about this? Will the temperature in the supply line drop? If the pressure doesn't change and the temperature doesn't change, does the enthalpy of the fluid coming in from the supply line change with time? You made the great observation. So if it doesn't come in with time, it doesn't vary with time, it's a constant with respect to time, you can pull it outside that integral. True? Once you do that, I recognize what this is, the integral m dot dt. So this whole side becomes the enthalpy, which is constant coming in, times the final mass in the control volume from the mass balance. So if I need to scoot just a little bit down, so if I rewrite this equation, I have the mass in the control volume when I close the tank times the internal energy in the tank and when I close the valve is equal to the enthalpy flowing in times the mass in the control volume when I close the valve. What can we do with the mass in the control volume when we close the valve? They cancel from both sides of the equation, which says that the internal energy of the tank when I close the valve is equal to the enthalpy flowing in. Okay? Well, let me try to help interpret this. If I have this tank, it's initially empty. Maybe I'm filling it with, I don't know, propane. I don't know the numbers on propane, but let's say it's I'm going to throw some numbers out here. What is the pressure in a propane tank? Typical pressure. I should know that. Boy, I can't. It's maybe I don't know. How many psi? I don't work in kPa in my mind. I should be able to look this up. It's gonna be a lot higher than 10 psi. 300, 200, 200. The 200 psi. Let's say the supply line is 300 psi. Enough to force it in, so the tank, I'm going to shut it off when it's 200 psi. I'm just throwing out some numbers. Let's say the supply line is 80 degrees F, right? So now I open that valve, in rushes, I'm watching the pressure on the tank, or I'm weighing it. That's usually what they do. They weigh it, if they have it figured out. When it gets up to the certain weight, and then it's 200 psi, and I shut it off, if I had a thermometer on that tank, what would it show? Would it show 80 degrees F? Would it show higher than 80 or lower than 80? The answer is right here. When I close the valve, the internal energy of that propane in that tank is equal to the enthalpy at which it flowed in. The enthalpy of that inflowing propane, HN, is equal to UN plus PVN. Right? So let's just take some guesses. The tank will be greater than 80 degrees F when I close the valve, equal to 80 degrees F when I close the valve, less than 80 degrees F when I close the valve. Which one? Greater. Because some of that PV energy, flow work energy, has to eventually be converted all into internal energy. Now I know if I filled it with liquid, and, there's some other little nuances to it, but essentially you're bringing in this is what you're bringing in, and that component has to be brought to rest. That's with the flow work. And so the final U2 will definitely be greater than U coming in. It'll be greater by the amount PD. All right. There's another great application problem for transient analysis. One is filling an empty tank, right? The other is emptying something where you're keeping it constant. So the other great application is if I have a tank, it's initially full. And I have a valve where I can leave it closed, and then all of a sudden I decide to start a process. I'm going to have a transient process. I'm going to empty some of the contents out of that tank. What I like to do is have a control volume around that tank. And in this case, this is a second great area of application of transient analysis. What I need to do somehow is to keep what's leaving constant. So maybe I keep the pressure constant, or maybe I keep the temperature constant. It's different wording of problems. Often they do it by putting a little heat transfer into the system. And they maybe dump a little heat early on, but then as it's starting to deplete, they curtail it or speed it up, put more heat in so that the pressure or the temperature stays constant in that tank. You just have to solve these problems. Go back to the most basic equations, conservation of mass, conservation of energy, and apply them slowly through the steps, do the analysis, okay? Ready to solve another problem? I don't feel like I'm communicating that well today. Are you getting anything out of this? Do you know, have I told you the recipe to get more out of my lecture as well as any other lecture in engineering? Did I tell you what to do before you come into the classroom? I did emphasize that. It will really help you. How many people think that, hey, I did read this chapter before. Hey, I did read this section before. Hey, I did struggle with what are they talking about on transient analysis. Oh, what he's talking about makes more sense now. Or some other people like, hey, this is the first time I saw it. I don't intend on looking in the chapter until, what was it, July the 9th? The night of the morning of the 10th. Not a good recipe. All right, we got to solve a problem. The problem with these problems, they're so long. I don't like this one. It's shorter. I probably could only solve one of them. If I get time, I can go back and solve the other. But less words, more work. So we have a 0.2 meter cube rigid tank containing saturated steam at 500 kPa. Saturated liquid fills 10% by volume of the tank. A valve at the bottom of the tank is open and liquid flows out. Heat is transferred to the tank so that the pressure remains constant. The valve is closed when no liquid remains in the tank. So right before it closed, there's still liquid, it's still in the bottom, and it's still flowing out. But as soon as that little bit of liquid flows out, you shut the valve. End of process. Determine the mass of liquid initially in the tank, etc. So let's go ahead and make a sketch. So we have a tank, and it's filled with a two-phase mixture, some liquid and some vapor. In the influence of gravity, liquid will settle to the bottom. Let's put it at the bottom. It's at a pressure of 500 kilopascal and a volume of the tank 0.2 meter cubed. Saturated liquid fills 10% by volume, so the volume that's the liquid is equal to 0.1 or 10% of the volume of the tank. I bet you the volume of the vapor is 90%, isn't it, of the volume of the tank? True? See that? So I can even say, okay, that's 0.02 meter cubed. This is 0.18 meter cubed. So some numbers I can doodle with and process in my mind as I read the problem statement. The valve is opened at the bottom of the tank, so let's put a valve right here. And just to show, hey, I can open and close it, there's a little handle to it. And the valve is closed when no liquid remains in the tank. There's also that heat transfer to the tank. Maybe I show it like this. Q dot is a heat transfer to the tank. It's happening per unit second, so it's a rate of heat transfer to the tank so that the pressure remains constant during that process. So this is what they're going to make constant during the process. The pressure is constant in the tank. All right. So now let's take a look. What is the mass of the liquid initially in the tank? We'll call that the mass in the tank at state 1. What about the mass of the vapor initially in the tank? Mass liquid 1, mass vapor 1. What is the mass of vapor in the tank at the end of the process? Mass vapor state 2. And the amount of heat transfer to the tank during the process, is that Q1 to 2? I try to encourage students to say, what is a good symbol for what I'm looking for? Pay attention to subscripts. Do you like these, or would you like to have a different symbol? And then what are the units? What are the units on what I'm looking to calculate? What is the unit on this one? Is it kilogram? Is this kilogram? Is this kilogram? And what is this? Kilojoule. So 3 kilograms with 1 kilojoule. All right. How do I find the first answer? A, part A, mass of the liquid initially in the tank.
We find a specific volume.
Yep. So state 1, let's think about states. S-T-A-T-E. I can spell state 1. We have the pressure at 1, 500 kPa. It's two-phase. Do I know the temperature at 1? Can I get U1 or V1? Can I get U1, H1, etc.? You know, thinking properties, I'm thinking, okay, can I go and get some of these values, U1, H1? All right, what about the temperature at state 1? Can I deduce it? If it wasn't explicitly given to me, can I deduce it? Okay, and what is it? You did your part, you said yes, now let somebody else shine. And they can now give it to us. What is it?
Oh, it's just a correlated pressure.
It's the saturation pressure for that substance, steam, at the 500 kPa.
It's 152.
152 degrees C?
151.9.
Close enough, 152. All right. What about the specific volume? Well, we have two specific volumes. We have the specific volume of the saturated liquid. We have the specific volume of the saturated vapor. True? So what's the specific volume of saturated liquid? 0.001093 meters cubed per kilogram. Okay, fine. Round off 926. Maybe I didn't pay attention too closely. Let me take a look. It's 500 kilopascal. How many bar is it? It's a 2.6. There. There it is, okay? And then V sub G, 0.3749 meters cubed per kilogram. So you get those out of the tables. At this point, we can solve for the mass of liquid initially in the tank. Let me try and do it up here. The mass of liquid initially in the tank is the volume of the liquid in the tank at state 1 divided by the specific volume of saturated liquid at state 1. And when I run that number, the mass of the liquid in the tank trying to save space comes out to be 18.305 kilograms. 18.3 kilograms. What is the mass of the vapor initially in the tank? Well, is the mass of the vapor initially in the tank equal to the volume of the vapor in the tank divided by the specific volume V sub G at 1? Most of the volume is vapor. Only 10% of the volume is liquid. So do you think the mass of the vapor will be greater than 18 kilograms, less than 18 kilograms, equal to 18 kilograms? You know, how will it compare, the vapor mass? And when I do that, I get half a kilogram, substantially less. Because look at the specific volume difference, it's huge. All right? So a lot less mass is in the vapor state. Okay, the mass of the vapor in the tank at the end of the process. Ooh, we can calculate part C right away. How am I going to get the mass of the vapor at the end of the process? Well, it's going to occupy the total volume of the tank, isn't it? And is it going to have the specific volume of saturated vapor at 500 kPa? The mass of the vapor is going to be calculated to be, you know what? I gave you the wrong number. 480, and this one is 0.533 kilogram. So actually, it's kind of interesting. There's more mass that's now in the vapor state. As the liquid left, the volume occupied by the liquid had to be occupied by some vapor. Now the hard part, the amount of heat transfer to the tank during the process. Calculate Q1 to 2. How am I going to do that? Energy balance, I like that. Thank you very much. Energy balance, and it's for a transient system. And so we have the rate of change of U. I'm just going to say it's only internal, not general E, where E is U plus KE and PE. With respect to time in the control volume is equal to the rate at which it's flowing in, no work, leave that 0, no mass flow rate in, the mass flow rate exit, taking with it its enthalpy exit. You separate, and so you'll get that the change in the mass internal energy in the control volume is equal to the Q dot dt minus HEM dot exit dt. Integrate. That HE that leaves has to be a constant, otherwise these are very difficult problems. The enthalpy leaving is always H of F. It's always saturated liquid at 500 kPa running out the bottom of the tank. That's why it's a constant, that's why it can be taken outside that integral. This is equal to the amount of heat transferred during the process from 1 to 2 minus H of exit, H exit, which is H of F, saturated liquid at 500 kPa. This rate, this is the integral of the mass flow rate exiting. That's going to be the mass in the control volume at the final state minus the mass in the control volume at the initial state. Isn't that how much, whoops, got to get the sign right. 1, 2. That's how much left. It started with this much. It ended with this much. That's how much left. Okay? Back on this side, we have the mass in the control volume final times the internal energy final minus the mass, control volume initial, internal energy initial. Does this equation look good to you? Yes or no? Okay, so there's a little bit of work, but we just got the answers to part A, B, and C. So the mass and the control volume final, that's the answer to part C. The mass and the control volume initial, that's the sum of A and B. True? Or one way you can do this term, this second term right here, put that is equal to the mass and the control volume initial of the saturated liquid. Put F there, and then use of F plus the mass and the control volume initial, the saturated vapor, G, times use of G. The mass and the internal energy initially in the tank is the sum of the contribution from the saturated liquid plus the contribution from the saturated vapor. All right, this is the mass, control volume state 2, use of 2. All right, equal to what I'm looking to calculate, Q1 to 2, minus H of F times that change in mass. That's the mass that exited. It started with so much mass minus the control volume. The sum at state 1 is, did I write that down anywhere? But you can add these up, right? That's the mass control volume state 1. This is mass control volume state 2. Mass control volume 1 minus mass control volume 2. Got it, got it. What's the enthalpy of the fluid exiting saturated liquid at 500? Got it. All of these, you look up saturated vapor, saturated liquid. This is all saturated vapor at the final state. And you calculate then Q, 1 to 2 is equal to 112.6 kilojoules. Too many digits, but there you go. Let me ask this question. Somebody says, don't put the valve at the bottom. Put the valve at the top now. So I change it up. I have the vapor up here. I have the liquid at the bottom. And I still want to maintain it at 500 kPa by heating it. But what I'm going to do is I'm going to put heat into it like that, Q, but I'm going to pull it off the top. And I'm going to start it at the same initial condition, and I'm going to end it at the same initial condition. Will the Q be the same? Would Q, the amount of heat that would need to be transferred into the tank to maintain the pressure always at 500 kPa, if I remove the vapor from the top instead of the liquid from the bottom, would the Q be the same? No. And it would be greater. Can you explain why it would be greater? That's right. The liquid that's coming out here is liquid. If it's coming out vapor. I'm going to have to vaporize it to get it to go out. Every bit of it comes out the top as vapor. It's going to be a lot more energy, isn't it? Here's another question. All of this mass that's initially liquid, every bit of that mass, is that what came out? Less. Why did not all of the liquid that was originally in the tank, why did that not all come out? Some had to vaporize to actually take the space of the liquid as it left. So some of it had to be vaporized. There's more we could say on this problem, but I think that's enough. Let me back up because we're done with this chapter, and I know we spent 3 days in it, but it's a very important chapter. What you have to be able to do is take some very general principles. These are very general in application. I recommend you always start with the most general to start with. Strike terms that are zero, Explain to yourself, why is that term 0? Be able to defend it if somebody challenged you. Maybe in a study group, study with other students. Have them challenge you. And you explain why that's 0. And the explanation is, well, I'm just following the example in the book, is not a good explanation. The transient analysis, it's difficult, it's challenging, work through them, go slow.